All right, Ryan, go ahead.
6D.
6C?
6D.
D. So we are asked to simplify. I mean, I don't know exactly what the wording is, but we are asked to simplify 1 over 1 plus cotangent squared. And one of the things we can do is we can change everything to sine and cosine, but we shouldn't be too hasty in doing that. That means we shouldn't rush in and automatically do that all the time, even though most of the time converting everything to sines and cosines is really the way to go. One of the items on the list, everyone, is to keep your eyes peeled for known identities. Now let me open up my formula sheet for you. And, you know, of course, there's more identities to come. It's a little intimidating when you look at all these identities. We've got all this other stuff below the identities that we've learned. But one of the sets of identities are the 3 identities on the bottom of the right-hand side of my screen here right now that are called the Pythagorean identities. And what makes them memorable is they have squareds in them. And the reason is they're derived using the Pythagorean theorem. So I see in the question 1 plus cotan squared. It's not, the question isn't 1 plus cotan squared, it's 1 over it. But 1 plus cotangent squared is equal to cosecant squared. And this is what I like to refer to as trigonometric enlightenment. When you see it, the light bulb goes on in your head. Because when you see that 1 plus cotangent squared, and I'm embarrassed to admit that I forgot whether it's equal to cosecant squared or secant squared. Cosecant squared. And on your formula sheet, I believe they're all thetas, at least so far. In a lot of the questions we do, they're math. But what this, or they're x. What this means, Ryan, is that when I see 1 plus cotan squared, if it's the same as cosecant squared, then I can choose to write 1 plus cotan squared as cosecant squared. So this becomes 1 over cosecant squared of x. I do know, and I'm hoping that you don't need to look at your formula sheet to know that cosecant is the reciprocal of sine, which means sine is the reciprocal of cosine. But, you know, don't take that to heart. If you have to look, look. Okay? But the bottom line here is 1 over something. I'm going to skip right to the answer here. How many of you see that since cosecant and sine are reciprocals, I could just write this as sine squared of x? Okay. If you don't see that, then what you're going to do is where there is a cosecant of x, you are going to put 1 over sine of x. And I'm not going to write an extra step. If cosecant is 1 over sine, cosecant squared is 1 over sine squared. And now you have this complex fraction, which we can simplify by multiplying the top and the bottom by that sine squared of x. And what happens here, of course, is the sine squareds on the bottom cancel, and you're simply left with the sine squared on the top. Does that make sense? Okay. And this will be kind of the frustrating thing. It's kind of the interesting thing as a teacher, because you will get very frustrated by a problem, and then when the solution is pointed out to you, you go, really? It was that simple? And sometimes it is. It's not always that simple, okay? Other questions? Go ahead, Makai. 10? So we want to simplify the expression. Well, it doesn't actually say simplify, but we are asked what's it equivalent to. So we have tangent of A, cos squared of A over secant of A. And one of the things I notice, I really think it's good advice at this level, is to look at your choices. It's multiple choice, right? So this gives us a clue that what we're going to want to do is get it all in terms of sine. And the starting point there, I think, is to rewrite everything in terms of sine and cosine and see what happens. And I know exactly what you probably did here to get to the answer, but then the answer's not there. Okay, it simplifies very nicely into something, but it turns out the answer isn't there. Tangent of A is sine of A over cosine of A. And then we're multiplying by cosine squared of A, which, just for the purposes of me explaining the canceling, I'm going to write the cosine squared of A as cosine of A, cosine of A. You don't need to do that. You know, if you know cos squared of A over cos of A leaves you with cos of A on the top, that's fine. I'm just expanding it out to be more explicit in my cancellation. This is over secant, which is 1 over cosine of A. So we have a complex fraction, everybody. By that I mean we have a fraction whose numerator and denominator is separated by this yellow line, but within the numerator and denominator of that big fraction, there are also other denominators. Now, we can simplify a little bit on the top, but that doesn't solve our problem of having the cosine of A on the bottom. So when I cancel a cos A on the top, I'm left with sine of A, cosine of A, over 1 over cosine of A. Everybody notice I'm working down. That's how you need to do this. You don't go equals, equals, equals till you get to the end of the page and then go next line equals, equals, equals. You work down. And if you get to the bottom of the page and you have room, start again at the top next to it on the right-hand side. So now I've got a complex fraction that I need to simplify, and I'm going to multiply the numerator and denominator by what I call the mini denominator in the large denominator. And I'm left with, after I cancel these cosine of A's, I'm left with something which is very satisfying looking at it in terms of the simplicity of it. It's sine of A times cosine squared of A. And you go, well, that's pretty simple. But then you remember that all of the choices have sine in them and no cosine. Now, I'm going to burden you with more information that you need to carry around. If I told you what is sine squared of theta plus cos squared of theta, we'll come back to the question in a second. If you see that, your trigonometric antenna should start picking it up and going, well, that's 1, right? That's a very common encounter you have when you're working with identities. This is equal to 1. But this identity is actually 3 identities. Because I could say that sine squared of theta is 1 minus cos squared of theta. So now you know what I'm telling you. I'm loading this on your back as well to carry with everything else. You need to keep your eyes peeled for 1 minus cosine squared of theta. It's not here, okay, in this question. I'm just saying if you're working on something and you see 1 minus cos squared, you can change it to sine squared. Similarly, if you're working on something and you see 1 minus sine squared, so all I'm doing is taking this identity which is on your formula sheet and I'm subtracting, for the bottom line, I'm subtracting sine squared. I get that. Now, this doesn't apply directly because we don't see 1 minus sine squared in this question. We don't see 1 minus cos squared. But this is a way for us to change cosine squareds to an expression that contains sines instead. And that means where I have sine of A times cosine squared of A, I can write sine of A times 1 minus sine squared of A. And I hope that you recognize that I believe that's choice D. It's not written exactly the same way as choice D. Choice D is sine of A minus sine cubed. But if we multiply this through, this is no different than having r times 1 minus r squared. You cannot rely on that crutch of changing out the trigonometric expressions for other letters, but it's the same idea. If you expanded this, you'd get r minus r cubed. If you expand this, you get sine of a minus sine cubed. Is that okay, Makai? Okay, good. Other questions? Zebi? For F? So we want to write sine of theta plus cotan theta cos theta as a single trigonometric ratio or the number 1. Some of these, when you simplify, everything's going to cancel and you're left with 1. Others will simplify so that you're left with only tangent or cotangent or sine, etc. I think if you go down your list of strategies that I've given you, let me rewrite this question. We have sine of theta plus cotan of theta, cosine of theta. If we go down our list of strategies, there's nothing to factor. I'm kind of jumping around here, but there's nothing to factor. There are no fractions to bring together. There is nothing in here that pops in my head and says, oh, that's equal to something else. Like, for example, if I saw cosine over sine, I would write cotangent maybe. I think the place to start is the first suggestion, which is to write everything as sine and cosine. And if I do that, every trigonometric ratio can be reduced to a combinations of sines and cosines. Cotangent is cosine over sine. And I mean, this is actually a new identity as of yesterday. Cotangent of theta is cosine over sine. But I think it's one that is fairly obvious after you've seen it a couple times. Tangent is sine over cos. Cotan is the reciprocal. And then we have multiplied by cosine. And again, look at how I've written that and organized it on paper. It's not just, I see stuff like this sometimes with students. I mean, I don't know what that means. It's all over the place. Your fractions are horizontal fractions, like the line separating the numerator and denominator should be horizontal. And in the case of the cosine that I'm going to underline in green, it's a numerator. It's not really a fraction. Well, actually it is a fraction. It's cosine over 1. So now I'm going to just multiply this stuff together, and I'm going to have sine of theta plus cosine squared of theta over sine of theta. And now I have fractions. Separate fractions are usually not what we want. There's going to be at least one case where we do want to do that, but if we bump into it, we'll talk about it. So I need to convert these fractions so they have the same denominator. If we have cosine squared over sine of theta and then the other fraction is over 1, this is pretty simple to do. I just need to multiply the numerator and denominator of this fraction by sine of theta. I didn't mention this, but the reason I'm multiplying numerator and denominator by the same thing is sine of theta over sine of theta, that thing in green, is equal to 1. And I multiply something by 1. I'm not changing the expression. Now I can put these together. How many of you see where this is going? As soon as you start to imagine putting them together, what you're going to see is that this will be over sine of theta. And in the numerator, we have sine squared of theta plus cos squared of theta. That should pop in your brain as being 1. Sine squared plus cos squared is 1. So we're left with 1 over sine of theta, which means that the answer is cosecant of theta. Again, a legitimate multiple choice question. That is equal to what? And I might have cosine theta, sine theta, cosecant theta, secant theta. Other questions? Go ahead, JV. E? Certainly. So we have cosecant squared. This is a good one. I get excited about some of this stuff. I know it's probably not that way in your brain, but this is a good one. This is an interesting one because there's at least a couple ways we can do this. There are many paths to go from where you are in the middle of that road home, okay, which is the answer. One of the things you might want to do, and you know, once again, everybody, I hope that you understand the x when you see x in a trigonometric expression. The x is not related to cosine on the unit circle. It's just a variable. I see squareds. And I know there are some Pythagorean identities that have things that are squared. So what can I do with this? Well, cosecant squared is 1 plus cotan squared. Let me grab this. I'm going to grab both of these. I guess I didn't need to grab both of them. The problem we are working on has cosecant squareds and cotangent squareds. So what I can do, and this is kind of what Sienna and I were discussing yesterday in the lesson, is I can choose to rearrange this identity to match something in the question, or I can rearrange the identity or part of the identity to match something in, or part of the question to match the identity. Like, it doesn't matter what you do as long as the substitution is algebraically valid. I would go the simplest route here and just say, since cosecant of theta is the exact same as 1 plus cotan of theta, then over here where I see cosecant squared of theta, and I might have misspoke and said 1 plus cotan theta, I meant 1 plus cotan squared of theta. I can just put 1 plus cotan squared of theta in for cosecant theta. And we're back to that, oh man, is it really that simple? Because it really is, if you see it. We can put 1 plus cotangent squared of theta, well, it's x, I suppose, minus cotangent squared of x, and cotangent squared of x minus cotangent squared of x is 0, so we're left with 1. Now, what if, did anybody do this problem and do it a different way? Did you get the answer? Yeah. I'm guessing what you did is you converted everything to sines and cosines. Yeah. Let's see what happens if you do that. So I'm starting from this line, and I would write 1 over sine squared of x minus cosine squared of x over sine squared of x. Is everybody okay with what I've done there? I've used the reciprocal trigonometric identity to change the cosecant squared. I'm going to erase this because I don't want you looking at it. I've used the reciprocal trigonometric identity to write cosecant squared as 1 over sine squared. I've used a quotient trigonometric identity to write cotan squared of x as cosine over sine quantity squared. And I lucked out here, didn't I? I won the denominator jackpot. The denominators are the same here, so I can put them together. And I get 1 minus cosine squared of x over sine squared of x. And as a teacher, I love it when things come together because we just talked about 1 minus cosine squared. Right? I don't know. That was number 10, I think. Wow. Yeah. Remember I talked about this? That you keep your eyes peeled for cos squared plus sine squared equals 1, but that means 1 minus cos squared is sine squared. And if we go back to this question, I don't know which one it was. If we go back to this question, that means that this top part right here is sine squared of x. And this is kind of what you were talking about yesterday, Sienna. We're kind of making the identity from the formula sheet fit what we have in the question. So we're left with sine squared of x over sine squared of x. And of course, a quantity over itself is equal to 1. If you don't see the quickest way to get there first, or if you don't see the quickest way to get there, it's okay. Go ahead. 5b. So suggestion number 1 on my list that I've given you is to write everything in terms of sine and cosine. It's done. So one of the suggestions, I've lost track of the order here, but one of the suggestions is for you to look out for recognized pieces of identities like 1 minus cos squared or 1 plus cotan squared, things like that. Well, there's nothing here that I recognize. There's no identity on my formula sheet that has a power of 4. One of them, the suggestions, is to put fractions together with a common denominator, but there's no common denominator. What we can do here, though, is we can factor. If I gave you, I'm going to take you back to grade 10. If I gave you x squared minus 9, you know it factors into x plus 3, x minus 3, because x squared minus 9, and we review this in Math 20, is what we call a difference of squares. And if you've had me for math when I teach you about difference of squares, this is how I explain it. Is x squared a perfect square? Yes. I would then say to you, if x squared is a perfect square, what is it the perfect square of? And it's the perfect square of x, which means you put x here and here. Is 9 a perfect square? What is it the perfect square of? Well, 3. So you put 3 here and here, and the pattern is that you multiply these together. And just to convince you of this, if I FOIL this out, I get x squared. My outer is 3x. My inner is negative 3x. And my last is 9. My outer and inner reduce to 0. So you get x squared minus 9. And I would always say, when you are multiplying factors that look like this, that are conjugates, you don't FOIL, you just FLA. You do first and last. Okay. So now, I forget who asked about this question. Zebi. Is sine to the 4 of theta a perfect square? Can you square something to get sine to the 4? Yeah, and what you square to get sine to the 4 is sine to the 2. So this is a difference of squares where I can put sine squared of theta plus cos squared of theta times sine squared of theta minus cos squared of theta. As a first step. You okay with that? Now, this is equal to sine squared of theta minus cos squared of theta. And the reason it's equal to that is that this is merely 1, right? Sine squared plus cos squared is 1. So that's kind of a weird, this is actually an identity, I suppose. Sine to the 4 of theta minus cos to the 4 of theta is sine squared of theta minus cos squared of theta. And I don't know, this is the thing about trigonometric identities. I don't know if that's the answer or not. It could be. But I could also put for an answer sine of theta plus cos of theta multiplied by sine of theta minus cosine of theta. Because sine squared minus cos squared in and of itself is also a difference of squares. This is like in Math 10 and 20, you're given stuff like this where you have x to the 4 minus 16. And you factor it as a difference of squares. And then you say, wait a minute, x squared minus 4 is again a difference of squares. So you get x squared plus 4. And then you have x plus 2, x minus 2. And, you know, in our analogy, with this analogy, when we take a look at what we did, this thing happened to be equal to 1, so it fell off. Is that okay? All right. Other questions? Go ahead.
Can you come up in the light to see if I did this question right?
Certainly. Which question number is it?
5A.
Okay.
I just want to make sure that I'm not doing something that is illegal.
Huh, I like that. No, it's good. But I want to talk about 5A on the board because I would have done it a little bit differently, and I just a little bit differently, okay? And I want to show this to you. We're asked to simplify this. Now, it turns out I look at this immediately and I see there's actually two other ways to do it. Factoring is an amazing tool at times because I have two terms here. I have secant of x sine squared of x minus secant of x, and I can factor secant of x out. That's not to say you have to do it this way. But if I factor secant of x out, what I'm doing is I'm bypassing that first suggestion of changing everything to sine and cosine. Because sometimes it's more convenient not to. What I am left with is sine squared of x minus 1. Now, I want to go back to that. We'll come back to this. I want to go back to that very important identity at the top of the screen here and remind you that that identity is actually 3 identities. But now what I'm going to tell you is that identity is actually 5 identities. And I want you to follow this because if you can pick up on this, if this rolls around your head and then finds a spot that you can retrieve it easily, then it will be very helpful. If sine squared of theta is 1 minus cos squared of theta, then cos squared of theta minus 1 is negative sine squared of theta. And there's so many ways that I could explain to you why that's the case. You could take this line right here and move the sine squared to the other side where it becomes negative, and move the 1 and the cos squared to the other side where they switch signs. I don't do that. What I say is, I know 1 minus cos squared is sine squared, so if these two things are opposite, if the 1 is negative and the cos squared is positive, then it's negative of sine squared. Similarly, negative cosine squared is sine squared minus 1. So what I'm saying, I suppose, is that if I'm telling you to keep your eyes peeled for this, then I'm saying, you know what you should also be doing? Keeping your eyes peeled for the negative of it. Now, I'm going to go back to that question because here I have sine squared of x minus 1, which is negative cos squared of x. And as a little detour, some of you may not be comfortable with everything I've just said, but everybody should be comfortable knowing that 1 minus sine squared is cos squared. Okay? Are you with me? All right. What can we do to this to make it 1 minus sine squared? We can factor a negative 1 out. If I factor a negative 1 out of here, then the sine squared will be negative. The negative 1 will be positive, and this is cos squared of x. By the way, Sienna, when I said I would have done it a different way, that's not what I would have done. Okay? And I'll get to that in a second. So what I have then is this, secant of x times negative cos squared of x. Secant is 1 over cos of x. So the cosine, one of the cosines in the cosine squared cancels with the cosine in the denominator of the first factor, and I'm left with 1 times negative cos of x, which is negative cos of x. Is that okay? Now, what Sienna did is she converted everything from this to sines and cosines. So she wrote 1 over cosine, and then she had times sine squared of x, and it's minus 1 over cosine. And she put them together with a common denominator. She recognized they're both over cosine of x, and she has sine squared of x minus 1 over cos of x. And I think what you did is you put in for sine squared 1 minus cos squared. Is that right? Okay. So she used that thing that I talked about in question 10 that says, look, if you want to get rid of sine squared, change it to 1 minus cos squared. This sine squared on the top becomes 1 minus cosine squared of x, and it's minus 1. It's over cosine of x. 1 minus 1 is 0. We're left with the same place. And it simplifies the negative cos of x. And actually, with the conversation we're having here is the same one we had yesterday. That it depends on how you look at it, because how many of you might just look at this and say this is negative cos squared? Because it's not 1 minus sine squared, which is cos squared. It's the other way around, so it must be negative. All kinds of ways you can weasel maneuver your way to the answer here. There was nothing illegal in what you did. Yeah. Other questions? Go ahead, Zebi. 6H. In light of everything I've just said, look at the top of this fraction in H. I have cos squared of x minus 1, and it's over tan of x. Now, this cos squared plus sine squared equals 1 thing is really valuable, but you have to try to wrap your head around it. Give me a second. If you can recognize there's lots of ways to do this. I'm trying to wrap my head around the best way to explain this. If you can recognize that this thing is going to be, based on this identity, an expression that contains sine squared of x and the number 1, then you can think ahead and say that if this expression right here is going to contain the number 1, then when I subtract this 1, the 1 will go away. So this is one way to look at it, is to say, I'm going to take this identity right here, and I'm going to rearrange it for cosine squared of x, and get 1 minus sine squared of x. And I'm going to put 1 minus sine squared of x in for cos squared of x. I'm really struggling here in my mind because this is not what I would do, but it's what I know some of you would do. Okay? So what we're saying is what I'm about to highlight in green is the same thing. Cos squared of x and 1 minus sine squared is the same. So this is going to become 1 minus sine squared. Okay. We're going to have 1 minus sine squared. Then we have minus 1, and it's over tan of x. I hope you see that we should probably write tan as sine over cosine. And I don't know exactly how to teach you that you should see that, but we're trying to reduce things down. We've already decided that this top is going to become something that's a single trigonometric ratio. It will be negative and it will be squared. So why don't we introduce sine of x and cosine of x on the bottom? We're just about done here because the top is negative sine squared of x. The bottom is sine of x over cos of x. When you write a fraction like this, I know I've talked about this before, but don't do this. Don't do that. Like, make it very clear where the main fraction is. I can multiply top and bottom by cosine of x to eliminate that pesky mini denominator. These cancel. I'm left with negative sine squared of x cosine of x over the sine of x, which survived the bottom, and one of the sines on the top and bottom cancel. Again, this is sine of x, sine of x. There's factors. We're multiplying everything, and that's the golden rule. You cancel if you're multiplying. And we're left with, what are we left with? Negative sine x cos x. Are you okay with that explanation? Okay, I wouldn't have done that. See, what I would have done, and it's a subtle difference, is I would have gone from here right to there. And I made a mistake here that is a very common one, forgetting to put the x, or maybe I erased it by accident. I mean, I look at cos squared of x. There's a squared up there that you can't see. I look at cos squared of x, and I know that it's equal to negative sine squared. Okay. Jason, you had a question? 13. Now, there's all this parsley sprinkled on the fish in this question. All this tan of x is not equal to 0, cos of x is not equal to 0, cotan of x is not equal to 0. The only reason we're saying that is because these are all things that appear in denominators. And you cannot divide by 0. It's not relevant to getting an answer to the question. I want to talk now about the fact that everything is being multiplied. And I kind of alluded to or hinted at that a minute ago, that if things are being multiplied, you can feel free to kind of cancel. I don't want to say wherever, but if I had this, I'm multiplying like everywhere across the top and the bottom. So anything on the top that's a factor with an identical factor on the bottom is fair game for canceling. And that's an important idea. On the other hand, if I had AB over C plus CA over B, boy, you cannot cancel anything in this expression. You have to put them together to a common denominator. From Math 20, everybody, you were only ever allowed to cancel if the thing you're eliminating on the top and the bottom is a factor of the top and a factor of the bottom. Okay? And a factor means the factor, is being multiplied by everything else. Okay. So I'm pointing out that what we have on the bottom here are factors. I'm going to rewrite this as an expression that has sines and cosines. And again, notice how I've very neatly organized things, that the cosine is, I know what happens in a textbook in an exam. you would see this. But I think it takes away from the rules that we have for fractions, which is you multiply across the top, you multiply across the bottom, or, I take back what I just said, although that's true. Don't multiply across the top, multiply across the bottom here. It's more important that you cancel things on the top with things on the bottom. And this is a complex fraction, but before we get to simplifying it, I can do this and I can do this. Right? Which means we're left with 1 over cos. That's it. We're done. Is that okay? By the way, this is 1 over cos, but it's also equal to secant of x, which might be the choice instead of 1 over cos. Go ahead, Ryan.
Just a question in general.
Okay.
How we were learning that sine square plus cos square equals 1,
Mm-hmm.
and then we can rearrange that for all different ways. Could we do it the same way for 1 plus tan square and equals secant square, and 1 plus cotangent square equals cosecant square?
Definitely. What I will tell you, so the question is, when I talk about taking 1 plus sine, I guess that's as big as it gets, sine squared plus cos squared equals 1, and Ryan said we can rearrange it in all kinds of different ways, at least 4 other ways, right? Don't start rearranging and taking the square root. That's possible at higher levels, but not here. Can we do the same thing with the other 2 Pythagorean identities? And the answer is yes, but what I'm going to tell you is you won't recognize it as often. But certainly, if you see 1 minus, let's see if I got this right, 1 minus secant squared. Let's imagine that we see 1, I did get it right. Somewhere in your work, you see 1 minus, I think I said secant squared of theta. Rather than taking this identity, is it 1 plus tan squared? No, 1 plus cotan squared equals secant squared? Tan squared. It's 1 plus tan squared of theta equals secant squared of theta. Rather than putting 1 plus tan squared here, which you could do that. I think what you're saying is, could you say, well, 1 minus secant squared is negative tan squared? And the answer to that question is definitely. And in my mind, that is simpler, and you're less likely to make a mistake with negatives if you do it that way. If you instead, so this is what it's equal to, negative tan squared. If you instead put in 1 plus tan squared, I can easily see people writing this and going 1 minus 1 is 0, so it's tan squared. Of course, I hope you understand that these 2 things are not the same, right? One of them's wrong. And the person who put in 1 plus tan squared forgot to put a set of brackets. 1 minus 1 is 0, but then you're subtracting tan squared. I think if you can see what you're talking about, Ryan, you're less likely to make a mistake.
Because I saw when we were talking about OE, I was thinking if we rearrange it like the first theorem, we could easily just got 1.
Yeah. When you're dealing with the Pythagorean identities, my analogy of going from that place in the middle of the road to the answer, to home, there's all kinds of paths. And what I would say to everybody is you're going to do whatever makes the most sense to you. You're not going to listen to a conversation that Ryan and I are having and go, oh, I'm going to see if I can figure out that way. If you've got a strategy that works for you, as long as you're not walking over acres and acres to get to the answer, stick with that strategy. Other questions? Go ahead, JV. Yeah, absolutely, sir. Once we go through all of the different strategies that are available to us, we see there's only one that could potentially work, and it's factoring. We cannot write everything as sines and cosines because it's already done for us. So I guess we can, but we don't have any work to do. There are no fractions to put together. I don't see in that expression anything that's popping in my head as being familiar from my formula sheet. There's only one thing left. Try factoring if possible. So I'm going to try to explain this in a different way. If we go back to the idea of a difference of squares, and I ask you to factor a squared minus 16, I feel as though, JV, you know this is a plus 4, a minus 4, right? But let's talk about the phrase difference of squares. The reason it's a difference of squares is it's a difference of two things. We're subtracting, so it's a difference. And it's a difference of a squared and 4 squared. So this is something I didn't do before when I explained this. I just kind of verbally said it. So a squared can be written as a squared. 16 can be written as 4 squared. And anytime you can write the two terms as one thing squared minus the other thing squared, it factors into the first thing plus the second times the first thing minus the second. So it doesn't matter what those things are, everybody. Those things could be and I've said this before, let's face it, the language we use for math is ultimately a bunch of scribbles on paper. It's more than scribbles because we understand what the scribbles mean. But they're just symbols that we put on paper. So if I said factor puppy squared minus diamond squared, is puppy squared a square of a thing? Yeah, it's a square of puppy. Is diamond squared the square of a thing? Yeah, it's the square of diamond. So then we can factor this into the first thing that's being squared plus the second thing that's being squared, multiplied by the first thing that's being squared, minus the second thing that's being squared. Now, just a side note here. The order in which you write these two factors doesn't matter, right? You could put puppy minus diamond first and then puppy plus diamond second. Does that make sense so far? Okay, so now let's try to turn it into this thing, or turn this thing into what we're talking about here. Is sine to the 4 of theta something squared? What would you square? And maybe I'll even back up a bit. What would you square to get r raised to the power of 4? R squared. There's a number of ways we can explain that. It's a power of a power, so if you're just a rule-oriented student, then 2 times 2 is what you do and you get 4. Or you could say, well, r to the 4 is r times r times r times r, so it's r squared times r squared, but it's r to the 4. And what that means in this case is that sine to the 4 of theta, which really maybe I should write another line here. Sine to the 4 of theta means this. And cos to the 4 of theta means that, right? So I think most of you are fine with having the exponent on the inner part where it's written. But that's what it means. So this becomes sine squared of theta squared minus the same logic we could use for cos to the 4 of theta, or cos of theta quantity to the 4, is that we would have to square cos of theta to get cos to the 4 of theta. So, I mean, compare what I have here in this line on the left, where I've left off, to the line that's right next to it on the right. We have something squared minus something squared. It's not a squared minus 4 squared, it's sine squared squared minus cos squared squared. But we're going to factor it in the same way. Whatever is in brackets here goes here, and whatever is in brackets here goes here, and then you put plus or minus. So this is going to factor into sine squared of theta plus cos squared of theta times sine squared of theta minus cos squared of theta. And at the risk of, overloading your senses with colors, this is what's going on, right? It's yellow squared minus blue squared equals yellow plus blue times yellow minus blue. Is this helping at all? Okay. We're back on more familiar ground, I think, now. This is 1. So we're left with sine squared minus cos squared. And if you wanted to, since this is still a difference of squares, you could factor it into sine of theta plus cos of theta multiplied by sine of theta minus cosine of theta. So my question to you, JV, is going from here to here, does that make sense to you? That is just another layer where we have sine that's being squared. So we put sine in the first two available positions, and we have minus cos that's being squared, so we put cos in the other two positions. Is that better? Okay. Other questions? Go ahead, Grant. 6D? E. Thank you. So cosecant minus sine. Cosecant of x minus sine of x. So if we go and we look at our list, there's nothing to factor. I'm avoiding the first item on the list because that's what we're going to end up doing. There's nothing to factor. There's no common factor. It's not quadratic. There's nothing like that. There are no fractions that we're seeing here that we can put together. There's nothing really there that lights up in my head as being part of an identity, like secant squared minus 1. Those kinds of things. So the only option I have is to rewrite everything in terms of sine and cosine. And if I do that, cosecant of x is equal to 1 over sine of x. And then we have minus sine of x. And this is over 1. And maybe I'll get back to that analogy thing. What is it? Your math teacher's been saying to you for years, oh, have you tried? What does that mean? It means you go to this list and you keep hammering away at some of these specific strategies. And even though, in other words, you don't stand there in the middle of the rain on the road and hope somebody's going to rescue you. You start walking. Even though we didn't have fractions we could put together here, we now have fractions we can put together here. And when I say put together, I mean add or subtract. Because if you're multiplying fractions, there's nothing you need to do because you're allowed to cancel everywhere. So the lowest common denominator here is the thing that we can convert both of those denominators to. And I can convert this denominator of 1 to sine of x by just multiplying the top and the bottom of that fraction, the numerator and the denominator, by a sine of x. And then I'm going to have, well, I'll show this extra step. I'm going to have 1 over sine of x minus sine squared of x over sine of x. How many of you would have not written them separately? You would have put them together in one shot, like at this point. Okay. Now we can put them together. You know, when we have 1 quarter minus 11 quarters, the reason we keep the denominator the same is because you're really literally adding 1 quarter and negative 11 quarters. You're adding quarters, so you're going to get quarters. Here we're adding sine of x's, whatever those are, okay? 1 over them. And we get 1 on the top minus sine squared of x. How many of you, by a show of hands, know exactly what we're going to do with the 1 minus sine squared? It's that Pythagorean identity, right? And this is a case of what Ryan and I were talking about, we've talked about a lot today. You take this identity that you know has a connection to this thing. It has a connection. It's sine squared of x plus cos squared of x equals 1. And if you're like me, you make this identity fit what we have there. So I say I want 1 minus sine squared. Well, it's x. I guess I shouldn't change variables. So I'm going to subtract sine squared from both sides and have cos squared of x. I end up with then cos squared of x over sine of x. Are you okay with that, Grant? How many of you see that if I gave you this as a multiple choice question, the correct answer could be cosine x cotangent x? You have to start seeing things that you wouldn't normally see. I look at this and I automatically imagine that it's cos of x, cos of x. It's over sine of x. Well, let's just put the sine of x over here because we're multiplying, so it doesn't matter where the factors go on the top and where they go on the bottom. Cosine over sine is cotangent, so it's cosine over cotangent. That's the frustrating thing about these identities is you can take an identity and take that mask off and put on a different mask on that looks different, and then change the mask again. You could have 5 or 6 different appearances. Other questions?